Welcome everybody for part B of plane wave propagation lecture. Today we're going to talk about wave propagation between two different media, dielectric interface under two conditions: normal incident angle equal 0, and oblique incident. In the previous lecture we studied the wave propagation between two media. One of them is dielectric, the other one is conductor. So today we are discussing dielectric interface. We're going to start by normal incident, which means the wave is propagating normal to the interface between two dielectric media. So media 1 and media 2. And in this case, we are choosing the wave to be propagating in the Z direction. Of course, E and H will be perpendicular. Both of them will be perpendicular to the interface, to the wave of direction of propagation, which means E and H, both of them are tangential to the interface. And we have three kinds of waves. We have the incident wave, when the wave propagates from media 1 to media 2 because of difference in dielectric constant, part of the wave will be reflected. So media 1 would have incident wave and reflected wave. This is very similar to the case of dielectric conductor interface. What is new here is that because this media is a dielectric media and it can carry electromagnetic waves, there will be some part of the incident wave transmitted into the media number 2, and we call it transmitted wave. This transmitted wave equals 0 in the case of conductor. If media 2 is a conductor, there is no electric field inside a conductor, so this is something new. And as we did before, the main idea to find out the conditions of the waves under this interface is the boundary condition. So we start by writing the different waves and then examine the boundary condition. So as I said, we have three kinds of waves here: incident, reflected, transmitted. The incident is propagating in the positive Z direction. For simplicity, we are taking the interface at Z equals 0. It can be at Z equal any value, but for simplicity, we're taking the 0 Z at the interface. So E incident, we choose the electric field to be in the AX direction. If you make it in the AY direction, no problem. It will be the same solution, and it has some magnitude. Then it is propagating in the positive Z direction. Beta 1 is the propagation or the phase constant for media number 1. HZ, so if this is AX and this is in the Z, positive Z direction, this will be in the positive Y direction. Second wave is the reflected wave. It is propagating in the negative Z direction. It has certain value for the magnitude, and it is its direction of the electric field is AX. Finding the reflected magnetic field, it would be in the negative AY. We are just applying the orthogonality between EH direction of propagation. Direction of propagation here is minus Z. So H reflected will be in the negative Y direction. The magnitude equals the magnitude of electric field divided by the intrinsic impedance, eta 1. Phase propagation constant is beta 1. When we go for the transmitted will be propagating in the positive Z direction. So we have negative sign here. The media 2 does have different value, so it's beta 2, different value of dielectric constant. So it's beta 2 and eta 2, different intrinsic impedance. And the direction of electric field is AX. It is propagating in the positive Z, so H transmitted would be the AY direction. So we have like the 6 components of the existing fields in our problem. We have 3 waves. Each wave does have E and H fields. So now, in order to find the relationship between the different components, we need to apply the boundary condition. So the incident is given, so we know we solve the problem as a knowing that E incident is known. Of course, we know the dielectric constant in both directions, so beta 1, eta 1, beta 2, eta 2 is known. What is unknown is E reflected, how much of the wave is reflected and how much of the wave is transmitted. This is what we are looking for. So we'll apply the boundary condition. In media number 1, we have 2 waves, incident wave and reflected wave. In media number 2, we have just the transmitted wave. And here you might be sort of like confused between T for tangential and T for transmitted, but it should be clear from the context here. So E1 equal E incident plus E reflected, and E2 is the transmitted, and the boundary condition for electric field is tangential component must equal one another. So the tangential component in media 1, which is the left side, equals the tangential component in media 2, which is the right side. The boundary condition for H, because this is a dielectric interface, there is no surface current on the interface, so the magnetic field on media number 1, which is the left side of this equation, equals the magnetic field on the media 2, which is the right side of the equation. So taking this equation and writing it below the first one, so this is the equation for tangential electric field, and here all the electric field is tangential to the interface, and this is the equation, rearranging the equation for tangential component of the magnetic field, and also all the magnetic field is tangential to the interface because we are propagating normal to the interface. So now we are writing boundary condition for electric field, boundary condition for magnetic field, and those are linear equations, and it's called like concurrent solution of 2 linear equations. So the easiest way here is just to sum the 2 equations. So E reflected will cancel out, and the left hand side will be 2 E incident. We put the 2 on the other side, so E incident equal half 1 plus eta 1 over eta 2 multiplied by E transmitted. So E transmitted equals this expression. So this blue term here is called tau, which is the transmission coefficient. Continue with the solution of the equation to find out E reflected. We can easily just subtract, for example, like subtract or just substitute this one, E tangential, E transmitted, and if we just subtract the 2 equations, we'll find E reflected in terms of E transmitted. E transmitted is known, just do the math, we'll find E reflected in terms of E incident, and this blue term here is called the gamma, which is the reflection coefficient. So gamma, reflection coefficient, tau, the transmission coefficient. And this is what we say we solved the problem of normal incident on a dielectric interface. Solving the problem means expressing the transmitted and reflected waves in terms of the incident wave and the parameter of the two medias here. So gamma, the reflection coefficient, can be positive or negative. Tau here is always positive, and in this case we have 1 plus gamma equal tau. In this case also you would examine the standing wave ratio S, which is maximum magnitude of the electric field divided by the minimum magnitude of the electric field, which we proved earlier that it's equal to 1 plus absolute value of gamma divided by 1 minus absolute value of gamma. So the standing wave ratio is always greater than 1, and also we showed that before the magnitude of the reflection coefficient is related to the standing wave ratio by this equation. And just a note here, these definitions are valid. All those definitions are valid even for lossy media. For lossy media, what will be the difference? The difference would be that eta 1 and eta 2 will be complex values. So tau and gamma also will be complex value. If we are handling a case of dielectric conductor interface, so media 2, if media 2 is a conductor, so eta 2 equals 0. So eta 2 equals 0 means that no transmission. So this is the case of previous lecture. Tau will be 0 and the reflection coefficient will be minus 1. And here, like, I recommend that you watch this video to visualize the standing wave ratio further. So when we have like a wave propagating in one direction and another component propagating in the reverse direction, the two waves will interfere, and here's like media number 1, it has incident wave and reflected wave. They interfere with one another to build a wave that is varying over time, but the envelope of the wave is like this, and the ratio between the maximum here, so the maximum here is 1.5, the minimum here is 0.5, and the standing wave ratio will equal 3 in this case. If we go here, this is the transmitted, it's one wave, there is no reflected wave. All the wave is propagating in one direction, so the standing wave ratio equal 1. The max and min magnitude is the same. One other problem, which is normal incident on multiple dielectric interfaces. So if we have media 1 here and we have like media 2 here, if we have media 1, media 2 and media 3, all of them are dielectric material, and we have a wave incident from media number 1 at the interface. The signal, part of it will be transmitted into the media 2, part of it will be reflected in media 1. The wave that is transmitted into media 2 will propagate, and it will like meet another interface. At the other interface, part of it will be reflected back into media 2, and part of it will be transmitted into media 3. Okay, the part that reflected back into media 2 will come here, it will face another interface. Part of it will go back to media number 1, and part of it will be reflected. So here in media number 2, there is a wave that's going back and forth between the two interfaces. At each interface, part of it will be reflected back to the media, part of it will be transmitted to the other media. at this interface, part of it will be reflected here, part of it will be transmitted here. So the waves that exist in each media here is infinite series of waves. So here we have incident, okay? So we have reflected, then we have a wave that is transmitted, reflected, transmitted. So a third component. The wave that is reflected here for the second time will go reflect here for the second time, come back and transmit it back for the second time. So there is multiple reflection back and forth between those two interfaces. At each reflection, part of the wave will go transmit here and part of the wave will be transmitted here. So we have like an infinite series of components. But anyway, because all the components that is transmitted from here to here are propagating in the same media, in the same direction as the reflected, we can collect them all into the reflected wave. Same thing for all the components that is traveling in the positive Z direction in media 3. It's all can be sort of like collected into one wave, which is the transmitted wave. Here in media number 2, we can collect all the components propagating forward into into 2 plus 2 in the positive direction, and all the components traveling in the negative Z direction into 2 minus components. And we notice here that we have two interfaces, interface 1 at Z equals 0, interface 2 at Z equal D. So when we're writing in media number 1, we have the wave in media number 1 equal E incident plus E reflected. We just know incident field and we know the properties of the dielectric materials, the 3 dielectric materials. So for media number 1, we have incident wave and all the waves component that are traveling in the negative Z direction are here summed up in this term. So we have a component propagating in the positive Z, another component was, we don't know this magnitude yet, propagating in the negative Z direction. H is related to E with the orthogonal relationship between E, H and direction of propagation. So it will have 1 over eta 1. This is positive and this is negative. If we go for media number 2, we have a positive Z component, a negative Z component. We don't know the magnitudes of both, but we know this is the expression. The electric field is in the AX. H2 does have this expression, component in the positive Z, so this is Z positive, and component in the negative Z, so this is negative. In the third media, we have just wave propagating in the positive Z direction, and E3 is unknown. So the unknowns that we are looking for is the reflected wave, the waves component, the 2 waves component in media number 2, E2 plus, E2 minus, and the transmitted component, E3 plus. Those are, like we have 4 unknowns, 1, 2, 3, 4 unknowns, and we have 2 boundary conditions, one at Z equals 0, one at Z equal D. We need to equate the tangential component of electric field at the 2 interfaces, equate the tangential component of the magnetic field at the 2 interfaces. So we have like 4 equations, all of them are linear equations, and we have 4 unknowns, so we can solve those problems, those 4 equations together to come up and find the solution, which means we find E reflected, E2 plus, E2 minus, E3. So this is how we handle a case of multiple dielectric slabs with normal incident. So now we'll come to the case of dielectric interface with oblique incident. And as we know, the oblique incident can be with perpendicular polarization, or it can be with tangential polarization. Perpendicular and tangential is with respect to the plane of interface, which does have the normal to the interface and the direction of the incident field. So anyway, there is some general cases here that we consider. For the boundary condition, like E tangential component 1, E tangential media 1, E tangential media 2, in order for this to be to have a valid tangential boundary condition on electric field, we'll find that the incident angle of incidence must equal the angle of reflection. So this is very similar to the case of dielectric conductor interface, and we call this Snell's law of reflection. Okay, also for the boundary condition on tangential component to be valid, to have a solution for it, we have N1 sine theta incident. N1 is the refraction index equal N2 sine theta transmitted. Angle always measured from the normal to the interface. So this is theta incident, this is theta transmitted, and this law is called Snell's law of refraction. Refraction is the expression for the wave that is transmitted from media 1 to media 2. We are saying the wave is refracted into media 2 and reflected back in media 1. So this is reflected back in media 1. This is refracted forward into media 2. The index of refraction equal C divided by phase propagation velocity. Sorry, the propagation velocity. So the speed of light divided by the propagation velocity in the media, which equals the square root of epsilon relative mu relative. If the media is non-magnetic, mu relative will equal 1. So the index of refraction will equal the square root of epsilon r. So this Snell's law of refraction does have this general expression here, and based on the nature of the material, it can be simplified to be expressed in this format for non-magnetic material. So this is general for any oblique incident between two dielectrics. Also, like one concept that is new, it's called the concept of critical angle or total reflection. So from Snell's law of refraction, if N1 is greater than N2, so epsilon relative 1 is larger than epsilon relative 2, so theta 1, which is the angle in media 1, will be smaller than theta 2, theta transmitted. So let us assume that we keep increase the incident angle. So the incident angle is getting like larger and larger. And of course, when this is getting larger, the also theta t, theta transmitted will get larger, but theta t is always larger than theta incident. So at certain value, theta transmitted will be 90. So it's called at this, so the wave, incident wave, part of it will be reflected with Snell's law of reflection, and the transmitted wave will be propagating on the surface, and we call this condition is a total reflection, because all the waves now is in media 1, nothing goes in media 2, just part is reflected and part is traveling on the surface. This angle, this incident angle that corresponds to 90 degree transmitted angle is called the critical angle, and its expression is sine minus 1 n2 over n1, and this happens only if n1 is larger than n2. So this is less than 1, so there is a real critical angle. So what will happen if we go beyond theta critical, if we go larger than theta critical? So now let us look into the refracted wave, the wave in media number 2. It's propagating in that direction in general, minus j beta 2 an, the direction of propagation in media number 2, dot r, which is the position vector. General expression in media number 2, we have an, the direction of propagation, equal az cosine theta t plus ax sine theta t. If theta incident is greater than theta c, the critical angle, we will find that sine theta t will be greater than 1. So if sine theta t is greater than 1, this is not like a physical angle, because we know that theta is always like bounded by, sine theta is bounded by 1. But in this condition, the mass would give us cosine theta t to be a complex value or imaginary value. So here, this will be imaginary. This will be some value that is positive to like comply with the Snell's law of refraction. It will be greater than 1, but we don't know. So the angle theta t is undefined, but we know sine theta t mathematically equal something greater than 1. So theta t would have a cosine that is complex, or like actually imaginary. So imaginary here means an imaginary component here. So imaginary multiplied by j. So j and j will equal minus 1. So this term will be a real component. When this is pure real, it means that it is like just decaying wave. So let us look into this further. So when cosine theta t is imaginary, this term, the phase propagation term, would have this expression. So cosine theta t is imaginary. So this would equal e to the minus alpha 2z. Okay, and we took the, so what is the meaning of this? It means that there is a decay in the z direction. What is the meaning of this? It means that there is a propagation in the positive x direction. So the wave is propagating on the surface and decaying into the z direction. That's why it's called a surface wave, or evanescent wave, or decaying wave. So there is no wave transmitted into media number 2. All the wave starting from theta c, theta incident equals theta critical, no waves propagates in media number 2. All the wave is propagating on the surface. And what is happening along the direction of z? It is just a pure decaying. So for cosine theta t, it's equal plus or minus. If we took the plus, this will be plus, and this means that there is a wave amplification, which is not physical, because if this is existing, if we go further, the amplitude of the wave will go to infinity, which is non-physical solution. So the only solution that we use is for the negative, which result in a negative sign here, which means there is a decaying wave along the positive z direction, and this is physical. This is a physical solution, because at infinity we would have a vanishing wave. There is no waves at infinity, and this is the solution that fulfill this general boundary condition. Okay, so now let us study the two different cases for perpendicular wave propagation. Oblique incident with perpendicular polarization. Perpendicular polarization means the electric field is directed normal to the plane of incident, which is normal to the direction of propagation of the incident wave, and normal or perpendicular to the normal to the interface, which is E is in the y direction in this case. So here we have three components. One component incident, or three waves: incident wave, reflected wave, and the new one here, new with respect to the case of dielectric conductor interface, is the transmitted wave. So in general, we write the expression for the electric field in the three media. From the expression of electric field, we get the expression for the magnetic field in the three media, and then apply the boundary conditions. We have one boundary condition for E tangential, one boundary condition for H tangential. It's important to know how to write the expression correctly and quickly. So E incident, it has a propagation, the direction of propagation is positive x and positive z. So it's sine theta x plus cosine theta z, and this is beta 1. H incident is just dividing by eta 1, and this is in the positive x direction, and this is in the positive y direction. So H is E cross, so we have E, H, and direction of propagation. So H will be direction of propagation, which is positive x, cross positive y, which is here does have the component along, so it's x cross y. We have this component in z, z cross y, which has a minus x. Okay, and this is propagating in the same, it's the same wave, so it's the same phase term. For E reflected, it has a component in the positive x and a component in negative z. So the wave propagating in the z direction is in the negative z. The wave propagating in the x direction is in the positive x. So again, we write the expression for HR. We'll find now that this is AX positive, this is AZ positive, the same propagation or like complex term. Writing E tangential, sorry, E transmitted. E transmitted is, it's very important, it's different angle, theta R equals theta I, but theta T is different. And also it's very important to remember that this is beta 2 because it's in media number 2, and this is eta 2 for media number 2. So now we have written all the field components. Now we need to apply the boundary condition. In media number 1, we have E incident and E reflected. In media number 2, we have just E transmitted. So we write down the tangential electric field. Here the electric field is normal to the plane of incident, but it is all tangential to the interface. So it's the total electric field in media number 1 equals the total electric field in media number 2. In order for this equation to be valid, the phase term must be the same. So theta I must equal theta R. This is Snell's law of reflection. And beta 1 sine theta 1 must equal beta 2 sine theta 2, which is Snell's law of refraction. From those, so we have like those two general conclusions that we discussed earlier. But now we have this equation, E incident plus E reflected equal E transmitted. Second boundary condition for H tangential. H tangential here is the X component. So if we remember, if we look here, we have H, X, and Z. We are interested in the tangential component to the interface, which is X and Y. There is no Y, so we just consider the X component of H. So H1X equal H incident X, H reflected X, and this equal H transmitted X. Writing the equations, we'll have this expression. So this is the boundary condition for tangential magnetic field. This is the boundary condition for tangential electric field. Solving those two equations together, there is only two unknowns, E reflected and E transmitted. Solving these two equations together, we have that the tau and this like perpendicular sign means it's a perpendicular polarization. Tau, the coefficient, the transmission coefficient here, which equal E transmitted divided by E incident. We'll have this expression, the gamma perpendicular, which is E reflected divided by E incident, would have this expression, and we find that we also can conclude that 1 plus gamma perpendicular equal tau perpendicular. So this is the solution that we have for this case of oblique incident perpendicular polarization for dielectric interface. So a question here, is it possible to have no reflection? Is it possible that we have gamma 1 equals 0? So let us see the possibility of this. If we want gamma perpendicular to equal 0, is it possible to have this equal 0 if the numerator equals 0? So we have no reflection. And this is the condition for eta 2 cosine theta equal eta 1 cosine theta. So at this specific angle, we call it like a Brewster angle, we have no reflection in media number 1. So we have, this is the first equation, and also we have the Snell's law of refraction here as a second equation. Solving those two equations together to find the theta I, we need to find theta I, incident angle, that cause this condition to happen. Solving those two equations together, just going forward, doing some math, we'll find that the incident angle that results in no reflection does have this sine square value. So it's called the Brewster angle, which is the angle that caused no reflection in media number 1. So if mu1 equal mu2, which is non-magnetic material, there is no Brewster angle. Why? Because 1 over 1 will equal 1. So this would be 0 and this would be infinity, and of course infinity, there is no angle corresponding to this. So the Brewster angle does exist if we have magnetic material. If it is a non-magnetic material, if mu1 equal mu2 equal mu naught, then there is no Brewster angle. And Brewster angle is the angle at which there is no reflection in media number 1. Okay, going for the second case of parallel polarization. So parallel polarization means the electric field is parallel to the plane of interface, which is the plane of incident. The plane of incident is defined by two vectors, incident vector and normal vector to the interface. So E is normal to here, and it's very important to write the expression for electric field correctly here. So electric field for media number 1 is propagating here in this direction. This direction is positive x and positive z, same as before. So the complex term is same as before, but this term is different here. So the field is propagating in that direction. So it has a component in positive x, a component in negative z. The negative z component goes with sine, the positive x component goes with cosine. So this is the incident field, and this is given. Theta I is known, E incident is known. Of course, beta 1, beta 2 are known. Writing the expression for the reflected wave. The reflected wave would be in this direction, which is positive x and positive z. So positive x and positive z. Direction of propagation is like reflected, so x is positive and z is negative, similar as before. To find the magnetic field, we also apply EHAN to find H, and we'll find that H must be in the Y direction. Okay, and similarly here we do this for HR, and the difference here, this is positive AY, this is negative AY. For the transmitted wave, it is not written here, let me draw it. So I just added a component to indicate the E transmitted. So the E transmitted does have like a component in positive Z and negative, so it's the component for E does have negative Z, similar to this one but with different angle, and positive X. This is the direction of the electric field. Okay, so this is the component of the electric field. It is propagating in the electric field does have a negative Z component and positive X component, and it is propagating in that direction, which is positive Z and positive X, and we find the transmitted magnetic field using also EHAN. So those are the three waves that does exist: incident, reflected, and transmitted waves. We continue with the same approach, writing the boundary condition for E tangential, and E1 will equal E incident plus ER. And here we need to find E tangential. E tangential is the X component only. So here we take the X component of E incident, X component of E reflected, X component of the E transmitted. Those are the tangential component. They need to equal one another. From the phase term, we'll have Snell's law of reflection, Snell's law of refraction, and the magnitude of those, like we have this expression. This is the boundary condition for E tangential. Write the boundary condition for H tangential. All the H is tangential because H is in the Y direction, so the phase terms are equal. The magnitude terms will give us this relationship. So we have now, like this is the second equation, solving for E tangential and solving for E transmitted and E reflected. We'll find the transmission coefficient for tau for parallel, and it does have this expression. gamma for parallel, it does have this expression 1 plus gamma equal tau multiplied by cosine over cosine. So this is different than before, but we have the transmission and reflection coefficient for this case of oblique incident with parallel polarization between two dielectric media. Is it possible to have no reflection? Is it possible to have no reflection here? Do we have a Brewster angle? We can write the expression and we can find that, okay, there is a possibility of having Brewster angle depending on the relationship between epsilon 1 and epsilon 2. So this was the last slide into this lecture. We have one homework which is due in a week, and thanks for attending this lecture and wishing you all the good luck in your exams. Thank you and see you in the discussion session.